Okay, so today's plan is to just finish the last couple examples in 11.2 on series, and then discuss the integral test 11.3. And the quote of the day today is that the outcome of any serious research can only be to make two questions grow where only one grew before. So I think this ties into the Epictetus quote from a few weeks ago. Conceit of knowledge gets in the way of learning. And I think the idea here is that there's a tendency to think that when we make a discovery, when we, whatever, read a journal article or something, that we've kind of solved a problem, right? That's kind of, we've capped that off and we know all that there is to know about it. And that's the end of the story. And that's very rarely true. So quite often through that process of discovery, sure, we maybe answered one question. But if we don't, as a result, see other questions come out of that, we're probably being a little short-sighted, maybe a little bit arrogant as far as what we think we know. So each discovery tends to lead to more questions. And, that's, I think, the better way of thinking about a new discovery, or really anything new that you learn, rather than seeing it as like, you've reached the top of a mountain and like, that's all that there is. It's kind of like you've reached a ledge on the mountain and you can, take a break and enjoy the success, but there's still a lot more out there to learn. Okay, so let's finish just these last couple examples in series. Just as a note, after we finish section 11.2, these last couple of questions, there will be a supplemental lecture on applications of geometric series and harmonic series. But we kind of need to talk about harmonic series before that will make a whole lot of sense. So we have a first question here on geometric series, and just recall the geometric series. So we had some I equals 0 to infinity of r to the I power, or this is 1 plus r squared, and so on. And we said this equals 1 over 1 minus r if r is between -1 and +1 open, and diverges otherwise. So we went through that proof and that discussion last time. And also recall that convergence of a series in general has to do with the convergence of the sequence of partial sums. So Sn, the nth partial sum, in this case would be sum I equals 0 to n of r to the I, or 1 plus r, and so on out to r to the n. This gives us a sequence of partial sums, Sn, n equals, suppose in this case we start at 0 to infinity. And just rehashing some of these things because it has been nearly a week and a half since we've seen this, and just want to remind you of some of these technical details. Whoops, S0, S1, S2, etc. And so this is 1 plus r, 1 plus r squared, and so on. And the question is, does this sequence converge? And again, last time we answered that it converges to 1 over 1 plus r if and only if r is in open -1 to 1. Okay, so let's look at how we can use this idea to write this decimal, this repeating decimal, as a fraction. So I'm sure you've heard that. Trying to zoom in a little bit here in my, there we go. The computer is not cooperating. I'm sure you've heard that repeating decimals are equivalent to fractions, or the irrational numbers or decimals that, never terminate and never repeat, something like that. So how can we actually start with a repeating decimal and write it as a fraction, write it as a ratio? And a ratio of whole numbers, of course. I suppose we could write it as a ratio by just writing 0.08 repeating over 1, but as a ratio of whole numbers. Well, let's think about what this actually means. So it means we write 0.08 and then just keep writing more 08s after that. So I see I have kind of a first 08, then a next 08, and a next, and a next, and so on. How could I think of what's going on here? Well, this first 08 is just 8 times something, right? It's 8 times 10 to the minus 2. That takes care of that first 08. What about the next 08? Well, the next 08 is just 8 times, well, I guess this would be 10 to the minus 4. And the next one, 8 times 10 to the minus 6. 8 times 10 to the minus 8, and so on. Now I can think of this as basically being like 8 times 10 to the minus 2 times 1 plus 10 to the minus 2 plus 10 to the minus 4 plus 10 to the minus 6, and so on. Now, one thing that I did here, I factored out something kind of from all of the terms in an infinite series. I'm being a little bit hand wavy here. If I wanted to be super careful, what I would do is I would write out the nth partial sum. I would do my factoring, and then I would look at the limit. I would investigate the limit of the nth partial sum. But it turns out that if I know that this is going to converge, if I know that this series is going to converge, things like factoring a number out like this are not problematic. So as an exercise, I would recommend going through those details, right off in the other side of your paper or something, off in the margin, what the details might look like if you work through the partial sums, and kind of convince yourself that what I'm doing here is not going to cause any problems, like we saw with 0 equals the sum of a whole bunch of zeros, and we could write those as 1 minus 1 and rearrange things, and we got like a 0 equals 1 kind of thing, right? So go through the details and convince yourself that that doing this isn't going to cause any problems like that. But if we have 8 times 10 to the minus 2 times this series here, but I notice that this series is just a geometric series. It's a geometric series with the ratio of 10 to the minus 2. 10 to the minus 2, 1/100th is indeed in minus 1 to 1. So this geometric series does converge. We have an 8 times 10 to the minus 2 in front, and it converges to 1 over 1 minus r. What can I do now? I guess I can multiply the top and bottom by 10 squared. 10 squared times 10 to the minus 2 on the top, they go away. 1 times 10 squared gives me 10 squared, and the 10 squared cancels with the 10 to the minus 2. Or this is 8 over 100 minus 1 is 99. And I think you can kind of see how this could be generalized for any repeating decimal, right? Where does why do we see that repeating decimals look like something over 9 or something over 99 or something over 999? Well, this is why, that our ratio for the geometric series is always going to be a power of 10, a negative power of 10. We're going to multiply top and bottom by that power of 10. It's going to be like 10 or 100 or 1,000. And then there's always going to be this minus 1 here. 10 minus 1 giving me 9, 100 minus 1 giving me 99, 1,000 minus 1, 999, and so on. So that's why this general, I want to say format, that's not quite the right word, but this general pattern that you might have recognized over investigating these repeated decimals in algebra or something in the past, that's kind of the underlying mechanics of where that comes from, why 9 or 99 or 999 typically show up, unless there's like a 3 or an 11 or something that like cancels it. You're often going to see in these repeating decimals 9s or 99, something like that. Okay, now let's look at the harmonic series. So this is the sum from I equals 1 to infinity of 1 over I, or 1 plus a half plus a third plus a fourth, and so on. Now, if we're not careful, we might look at this series and say, well, the individual terms do go to 0. Well, I remember my test for divergence. Does the test for divergence say that this converges because the terms do go to 0? No, I have to be very careful. My test for divergence says if my terms do not go to 0, then the series diverges. If the terms do go to 0, the test for divergence, the conclusion doesn't apply. So the terms going to 0 is a necessary but not a sufficient condition for convergence. The terms do go to 0. This might converge, but it might not converge. And in fact, my claim is that even though the terms go to 0, the series diverges. So one way that I tend to think of series convergence is the terms have to go to 0 fast enough. The terms have to get small enough fast enough in order to converge. Let's make an argument that the harmonic series diverges. So let's consider Sn, sum I equals 1 to n of 1 over I, or 1 plus 1/2, and so on, plus 1 over n. Let's consider this nth partial sum and see what happens to it as n goes to infinity. And we might kind of suspect, I mean, this isn't a proof, but we might be thinking, okay, if the series diverges, probably what's going to happen, because we're adding a whole bunch of positive numbers together, probably what's going to happen is we're going to end up wanting to show that Sn goes to infinity as n goes to infinity. So this is in the back of our mind. This is kind of our guess at where we're going to be heading here. So question, does Sn go to infinity as n goes to infinity? And that is indeed what we will show. Right? It doesn't seem likely that we're going to get a series where the partial sums bounce around too much or something like that. These are all positive numbers added together. This is kind of my guess at where this is going to break. Well, showing that Sn goes to infinity is kind of annoying, but if I could find a lower bound for Sn that's a nice, clean function, and if I could show that that function that's a lower bound for Sn goes to infinity, then Sn has to go to infinity as well. Let's try to do something like that. So I can think of Sn as just being a bunch of numbers added together, but I could also reframe it in terms of maybe areas. So let me draw a two-dimensional plot here. And let me look at my first area, 1, the first term of my sum. If I want a box of width 1, it's going to have height 1 in order to have area 1. If my next box that's going to sit between 2 and 3 has width 1, in order for it to have area 1/2 to tack on the next term, it's going to have height 1/2. Between 3 and 4, my box is going to have height 1/3, and so on. So these points are going to look like 1, 1, 2, 1/2, 3, 1/3, and so on. Okay, so the box to the right of 1, or between 1 and 2, gives me the area 1, or contributes this term 1. The box between 2 and 3 contributes the 1/2. The box between n and n plus 1, this is going to be point n, comma 1 over n. It's going to have area 1 over n for its area. That's going to contribute that last term. So I have all these boxes, all of these boxes in between here, and then my box between n and n plus 1 on the horizontal axis, that's going to be my last box. So I am adding up box areas from 1 up to n plus 1. So the area under these boxes, or the area under this piecewise function, this piecewise constant function, that's height 1 in between 1 and 2, and height 1/2 in between 2 and 3, and height 1/3 in between 3 and 4, and so on. This is just a piecewise constant function that we're looking at the area below it. Well, can I think of a function, a nice function, or one that's kind of easy to deal with, that just basically connects these dots, which I didn't connect very well, but I guess I would get a bad grade in art class. But can I think of a function that connects these dots, like 1, 1, 2, 1/2, 3, 1/3? Well, this function is just 1 over n, or sorry, 1 over x. So let's now call this the x-axis. So Sn is just a piecewise constant function going from x equals 1 to x equals n plus 1. And it's the area under that. I guess I said that a little wonky. Sn is the area under that piecewise constant function. It's the integral of that piecewise constant function. I know for each of these pieces, the area under 1 over x is less than that, because 1 over x intersects a given box at the left endpoint. The box has constant height, and 1 over x is decreasing everywhere on this interval. So the integral of 1 over x on each of these segments, 1 to 2 or 2 to 3 or 5 to 6 or whatever, the integral of 1 over x on that interval is going to be less than the contribution to the sum over that interval, than the integral of that constant function over that integral, because 1 over x intersects at the left endpoint and is a decreasing function. So I note that Sn, the area under all the boxes combined, is bigger than or equal to, or in this case, I suppose we could pretty safely say strictly bigger than, although it doesn't much matter, the area under the 1 over x function. In other words, integral from 1 up to n plus 1, 1 over x dx. But this is just what? Log n plus 1 minus log of 1, but that's 0. So what have I shown? I've shown that Sn is bigger than log of n plus 1. What do I want to do? I want to let n go to infinity. As n goes to infinity, though, I note that log of n plus 1 goes to infinity as well, and Sn is bigger than log n plus 1 for any given n. So Sn, my sequence of partial sums, has to go to infinity as n goes to infinity. This means the harmonic series diverges. This is actually a very important counterexample. So a lot of times if you're trying to remember a theorem, or if you have something a little bit wonky and you're thinking, wait, is this the way it works or is that the way it works? Ask yourself, does it work for the harmonic series? We know that the harmonic series diverges. We just proved that. And this is what it is. And so if I was thinking of my test for divergence and asking, well, wait, does it work the other way? Maybe I'm thinking it could be true that if the terms go to 0, then the series converges. That we didn't prove that that was not true, but this provides a counterexample. This provides an example of a series where the terms do go to 0, but where the series does not converge. So the test for divergence really is only a one-way test. Very important. Or in other words, the terms going to 0 is a necessary condition for convergence. It needs to happen in order for the series to converge, but it's not a sufficient condition. Just knowing that the terms go to 0 isn't enough for the series to converge. They have to go to 0 fast enough. And in this case, in the harmonic series case, they do not go to 0 fast enough for it to converge. And then as kind of a side note, my red curve should go actually out here to n plus 1. As a side note, I found a lower bound for Sn. That was all that I needed to prove what I wanted to prove. Could I find an upper bound for Sn? I actually could. I could shift my 1 over x function to the right 1 unit so that it went a little too far there. I could shift it to the right so that it intersects all of the right endpoints, and then it's always an overestimate, and then I have to add 1. So I have to have a plus 1 here just to take care of this left-hand area. And I can see that Sn is going to be less than 1 plus, and what's this? This is the integral from 2 to n plus 1 of what? Well, if I took 1 over x and shifted it to the right one, that's 1 over x minus 1. Right, when x equals 2, then we're at height 1 over 2 minus 1, or 1. But this is 1 plus log of x minus 1 from 2 to n plus 1. Or this is 1 plus log of n plus 1 minus 1 is log of n minus log of 2 minus 1, which is just log of 1, or 0. So I see that Sn is bounded below by log of n plus 1, and it's bounded above by, it's not letting me write it over there, but 1 plus log of n, or log of n plus 1. So this gives me an upper and lower bound for Sn. And in one of the applications in the supplemental video, we'll use the upper and lower bounds to get an estimate. So we can get an estimate for the size of the partial sums of the harmonic series by using logarithms. But of course, the harmonic series itself does not converge, it diverges. Any questions so far? Okay, so again, harmonic series, super important and useful, really for counterexamples, because it's a series that we might at first look at and think that it converges, but we see that it diverges. Geometric series, very useful in just a lot of applications. There's a lot of applications where geometric series comes up. Okay, so moving on to the next section, 11.3 with the integral test. This idea of the harmonic series also gives us maybe a more general idea. If I'm looking at evaluating the convergence or divergence of a series, maybe I could consider an integral that's kind of related to that series. And if that integral converges, then the series will converge. And if the integral diverges, the series will diverge. Maybe that would be my kind of my guess. Now, something that I notice, I mean, up here, I didn't get like Sn equals something. I kind of got some kind of bound, right? This was like a fuzzy kind of idea here. So I'm not going to be able to use an integral to figure out the sum of a convergent series, at least, not usually. So the integral test, the goal is not to get me the sum of a series that converges, but the goal is really just to help me evaluate convergence of the series. So what is the integral test? So we have a theorem called the integral test, and it says that if a function f is a continuous, positive, and decreasing function on closed 1 to infinity, and if an equals f of n, so if my terms of my series correspond to these function evaluations, similar to what I drew above, then the series is convergent if and only if the integral from 1 to infinity, f of x dx, is convergent. And again, we're evaluating this convergence of the integral on the basis of the definitions that we had back in chapter 7. So if you don't remember exactly what those definitions were, go take a look back and make sure you're familiar with those. So we see convergence of a series is equivalent to convergence of the integral, but importantly, under a couple of assumptions. F has to be continuous, positive, and decreasing. Okay, so let's use the integral test. I'll clean up my scribblings up here. Let's use the integral test to show that this series is convergent. Sum n equals 1 to infinity of 1 over n squared plus 1. So here, let's consider f of x equals 1 over x squared plus 1. If we call an 1 over n squared plus 1, this is, of course, f of n. So this checks out. Is f continuous? Yes, it is. Is it positive? Yes, it is. Is it decreasing on 1 to infinity? Yes, it is. Okay, so all of our assumptions are satisfied. F is continuous, positive, decreasing on 1 to infinity. And an equals f of n. So let's evaluate the convergence or divergence of the integral of f. I'll write it this way. It's maybe a little more recognizable that way. Integral 1 to infinity of 1 over 1 plus x squared dx That's arctan x from 1 to infinity. And I know this converges. What does it converge to? Well, I guess it converges to what? I guess pi over 2 minus arctan of 1. So we can conclude, we can say by the integral test, the series sum n equal 1 to infinity of 1 over n squared plus 1 converges. So we can make this statement. Note that what we're not saying. So we're not saying that the value that we got out of evaluating that integral is equal to the sum of the series. Right? We only use this integral to determine convergence or divergence of the series. Really, what we're kind of saying is that the tail of the integral kind of looks like the tail of the series, and if one converges, the other one should too. But we're not, we saw up here, we're really not, we're not finding the exact sum of the series. This might not even be that great of an estimate of the sum of the series. So we don't even really want to say that it's approximately this number. It might not be that great of an estimate at all. It's just that the tails have to look pretty similar. Okay, so let's look at something like this. Sum n equals 2 to infinity of 1 over n log n. So I have a couple of things here. One is that this starts at n equals 2. Does that matter? Well, no. Remember, convergence is a feature of the tails. If I, start 1 or 2 increments later, if I chopped off these 2 boxes, does that affect whether this is going to converge or diverge? Well, no, it doesn't. If this did converge and I got a sum for the series, it would affect the sum, but it wouldn't affect whether the thing converges or diverges. Okay, so starting at n equals 2, not a big deal. Why do we start at n equals 2? Well, because if we started at n equals 1, we'd have log of 1 is 0 on the bottom. So f of x equals 1 over x log x on 2 to infinity. Is this continuous, positive, and decreasing on 2 to infinity? Yeah, it is. Yeah, no problems there. So our assumptions are satisfied. And then if we integrate 2 to infinity, one over x log x dx, what do we get here? Well, this might, look like it's been I don't know, a little while since we've done integrals, right? Integration techniques. But if we think back, this might look like a tough integral, but what was one of our earliest techniques? Substitution. So if I think simple first and not try to jump to integration by parts or something, if I think simple first, can I do a substitution? Yeah, sure. U equals log x du 1 over x dx will work just fine. So these bounds relate to x. So I have a 1 over u. That takes care of the log x. 1 over x dx. That's a du. I'm going from when x is 2, u equals log 2. And as x goes to infinity, u goes to infinity as well. So this is log of u from log 2 to infinity. And I'm being a little bit imprecise with the notation here. throwing these infinities around like this, but we know what this means is this means take the limit as u goes to infinity. And I see that this goes to infinity. Right, log u grows without bound as u goes to infinity. So my integral goes to infinity. In other words, I can say since integral 2 to infinity of 1 over x log x dx goes to infinity or diverges, this series some 1 over n log n diverges. So kind of as a side note, integral 1 over u du turned into a log of u. And that log of u is what shot off to infinity. What if I had, say, 1 over u squared? That would integrate to like a 1 over u. And then as u goes to infinity, that goes to 0. That would converge. What if I had a 1 over u to the power 1.5? I would still be left with the square root of u on the bottom. So that would still converge, right? What is u related to? U is related to the log x. So something like 1 over n log n squared, well, that should converge. Or something like 1 over n log n to the 1.5 power, that should also converge. Something like 1 over n log n to the first, of course, does not converge. We just saw that. Or 1 over n log n to like the 1/2 power, 1 over n square root of log n, that also should diverge. So that's what this next idea looks at, looking at p series. So the claim is that sum n equals 1 to infinity of 1 over n to the p is convergent if and only if p is bigger than 1. So let's prove that it converges if p is bigger than 1. So we'll prove the one direction. If p is bigger than 1, this converges. And then we'll look at the other direction. Okay, so what about if p is bigger than 1? Then if we consider some n equals 1 to infinity of 1 over n to the p, let f of x equals 1 over x to the p, where p is bigger than 1. So this is like 1 over x squared or 1 over x cubed, something like that. So no trickery going on here. It's not like 1 over x to the minus 1. It's really just like an x. So if I think of 1 over x squared, 1 over x cubed, 1 over x to the p, where p is bigger than 1, this on 1 to infinity, this is continuous. This is positive, and this is decreasing. The integral test applies. So let's consider integral 1 to infinity of 1 over x to the p dx. And from chapter 7, I guess not, equals, I'll say. From chapter 7, this converges if p is strictly bigger than 1. Since p is strictly bigger than 1, my integral converges, and therefore my series converges. Okay, so I see that if p is bigger than 1, my series converges. What about if p is not bigger than 1? Well, let's look at two other cases. If p equals 1. Well, that's an easy case. That's just sum n equals 1 to infinity of 1 over n. That's just the harmonic series. And we've already shown that diverges. Okay, so if p equals 1, this series diverges. What if p is less than 1? Well, let's maybe do two subcases here. If p is less than 0, that's also a pretty easy case to knock out. If p is negative, then 1 over x to the p equals x to the absolute value of p. Right? If p is like -1, 1 over x to the -1 is like x to the +1. And then the integral of x to the absolute value of p, pretty clearly that's going to shoot off to infinity, right? Or even if I just look at, I should have n's down here. I wanted these to be n's. There we go. Because we're looking at the terms of the series. So I could think in terms of the integral, and the integral is going to shoot off to infinity. So I think the series probably should as well. I do have to be a little careful here, though. I don't want to apply the integral test directly because I don't satisfy all of the assumptions, particularly being a decreasing function. But in this case, it's actually pretty easy. Clearly, this does not go to 0 as n goes to infinity. N or n squared or n cubed or something, as n goes to infinity, they don't go to 0. So this diverges by the divergence test. So what about if p is between 0 and 1? And I guess we could so I guess we could include 0 in here as well, I suppose. That also diverges by the divergence test. Now, what if we still have to knock out, what if p is between 0 and 1? So then what do we have? We have sum n equals 1 to infinity, 1 over n to the p. So 1 over n to the p, where p is between 0 and 1. So this is like 1 over square root of p, 1 over square root of n or something like that. If I take f of x equals 1 over x to the p, so something like, say, 1 over square root of x, 1 over cube root of x, 1 over x to the 0.7 power. On 1 to infinity, this is continuous. This is positive, and this is still decreasing. Something like 1 over square root of x, that's still a decreasing function. So I can actually use the integral test here as well to show divergence. So what can I say here? I can say since integral 1 to infinity of 1 over x to the p dx diverges when p is in 0 to 1, sum n equals 1 to infinity of 1 over n to the p diverges when p is in 0 to 1. I could have lumped this case in with the other integral test case, but I wanted to kind of handle the divergent parts separately just for cleanliness, but it would probably have been a little more elegant to wrap this bit down here with p between 0 and 1, and we could even wrap p equals 1 in with this initial integral test argument. But here we saw that if p is bigger than 1, we get convergence. Otherwise, we get divergence. If p equals 1, if it's equal to 0, if it's between 0 and 1, or if it's less than 0. Any of those cases, we get divergence. Any questions on this? One of the things that I think folks struggle with in series particularly is that sometimes we have things like, say, the geometric series, where we have a test in a manner of speaking. We recognize that something is a geometric series, and we can talk about its convergence or divergence. And that results in a number. There's like a number that's associated with that test, 1 over 1 minus r, that if the series converges, that's the sum of the series. Again, we have other tests like, this argument related to the harmonic series, or arguments like this from the integral test, where we do get kind of a number that comes out. But that number is not the sum of the series. It's just the only purpose this number serves is to verify to us that the integral does converge, and therefore the series converges. It's not saying that this is the sum of the series. And I think the other thing that folks get a little confused on in these topics is each of these theorems has an assumption and a conclusion. If we're not very careful, very cognizant of our assumptions that go with each theorem, we're going to be applying conclusions where we ought not. Again, for instance, the test for divergence, we have to be very careful. Like, if the terms don't go to 0, then the series diverges. That's what it says, but that's all that it says. It doesn't, you can't add a bunch more onto that. Or the integral test, if we have a function that's not decreasing, we can't apply the integral test. We have to find another approach. So down here, I didn't apply the integral test in this case because my terms don't go to 0. My terms don't decrease. So I had to look for a different approach, and I said, okay, I can use the divergence test here. So I could use the divergence test in this case, and then I could use the integral test in the other cases. And then for this last example, we investigated this a little bit already, but let's use the ideas of this p-series test to examine this kind of similar type of p-series, 1 over n log n to the p. We kind of hinted at what the answer might be, but let's go through and do that carefully. Okay, so for what values of p is this series convergent? Well, let's consider this function f of x. All right, so what do I have here? I have 1 over x log x to the p on 2 to infinity. And I'm interested in the integral 2 to infinity of 1 over x log x to the p dx. And again, just like earlier, I saw that I could use a substitution. U equals log x. Du is 1 over x dx. This is going to be integral. So we start at x equals 2. So u starts at log 2. And as x goes to infinity, u goes to infinity. We have 1 over, well, log x to the p is just u to the p. 1 over x dx is du. I see that this is really just a P series in disguise, isn't it? I get the same kind of integral that I got up here. I mean, I have a little bit of a difference in that I'm not starting at 1 anymore. I'm starting at log 2, but that's really the only difference. So this will converge if and only if p is bigger than 1. We could maybe even recognize a pattern here, and we could ask something like, what about some, and I think I would have to go to n equals 3 here. What about something like 1 over n log n times log n to the p? So this log of n is all getting raised to the p. Well, we could kind of imagine that we're going to end up with an integral like 1 over x log x. We're going to use the substitution u equals log x to give us a 1 over x log x. And we're going to again end up with a 1 over u to the p kind of situation. And again, we're going to get converges if and only if p is bigger than 1. We could continue on with this pattern. We could have an n, a log n, a log n, and then a log n to the p on the bottom. And it's going to have the same kind of criterion. So there's kind of a sense in which the harmonic series is the borderline series between convergence and divergence in the sense of the p series, right? This converges if and only if p is strictly bigger than 1, p equals 1. That borderline between convergence and divergence is the harmonic series. But it's kind of like a soft border, right? Because of functions that look like this, that p equals 1, that harmonic series is the dividing line between convergence and divergence. But we could come up with functions that look a little bit different, like these ones, that are smaller than the harmonic series in a sense, in the sense that each of the terms of a series like this one or like this one is going to be smaller than, with p equals 1, is going to be smaller than each term of the harmonic series, but these series still diverge at p equals 1. So it's kind of interesting, right? The harmonic series, and from one perspective, is kind of like the borderline case, but you can, add in a little bit more nuance. You can kind of fine tune things a little more. And so the harmonic series isn't like a hard line between convergence and divergence. You can get series where each term is smaller than harmonic series, they still converge, but you have to go to a different type of function to actually see that. Okay, so that was what I had planned for today with the integral test. Are there any questions on anything?